Great. So, um, usually I like to tell people a little later than when we are live because, it's more natural and fun and random. So we've been live for the past 30 seconds.
Okay.
All right. Karen and Andre, so excited to talk to you today. As usual, if Mariam was here, she would have us like dance or something at the beginning. She likes to do that. But since the three of us are physicists and nerds, we're going to just ignore that. Unless you want.
All right.
Instead, we're going to
No,
talk about what we do.
I'm quite okay with that.
Oh, yeah. Exactly. I'm drinking my usual black tea. How about you, Andre?
Yeah, I have dark roast coffee, black as well.
Do you make it yourself? Do you brew it?
Well, yeah, I have a coffee machine that's like fully automated.
Sounds good. How about you, Karen?
I'm beverageless at the moment, but usually, I'm a tea drinker myself. Yeah.
All right. What kind of tea do you prefer?
I'm a classic kind of Canadian tea drinker. I drink Red Rose, Orange Pico tea. I grew up many years with my grandmother, and that was the tea of choice. So I'm kind of in that habit.
Sounds good. Hi, everybody who's joining us today. Thanks for joining. And hopefully, we're going to have a sufficiently random but educational conversation about environmental data science. But I like to start this conversation by, both Andre and Karen have studied and researched environmental physics or climate physics. So maybe you can do a quick intro, each of you, and then we can talk a little about why do we even care about modeling environment, and then we'll start a conversation there. Maybe Andre can get us started.
Yeah, sure. So I started in physics in my undergrad, but I've always been interested in atmospheric science. And actually, for a while, I didn't even know you could study atmospheric science. Right? And then as I sort of learned more and I took a remote sensing course, I got more into earth sciences and I realized you can study atmospheric science, and it combines basically everything that I think is cool about physics. Remote sensing, radar, satellites, fluid dynamics. And so then I changed into meteorology and I did my master's in meteorology and actually learned a lot about numerical weather prediction as well. And maybe we'll get a chance to talk a bit about that. And then I went back into physics and at U of T and did my PhD in regional climate modeling. And since then, I've moved more into like more general environmental science. And I've worked a lot with hydrologists. I do hydrological modeling of climate change impacts, but all from a numerical modeling perspective for the most part. I've dabbled quite a bit in machine learning as well, but really the core of what I do is sort of high performance computing and numerical modeling, climate, and also hydrology or system.
Yeah. Andre and I have somewhat of an overlapping background, I guess. We both were PhD students at the same time in U of T and atmospheric physics. But I come at it from a little bit of a different direction. So as a young person, I was really interested in environmental issues and environmental challenges, and I ended up doing an undergraduate degree in engineering because I was thinking about renewable energy and sort of going that direction with my studies and getting into sort of climate change solutions from that perspective. But then I took a fluid dynamics course and I was basically kind of hooked on fluid dynamics at that point. And so, started to think about environmental fluid dynamics. And, I thought about a variety of things. You can think about pollutant transport in aquatic systems. You can think about, atmospheric fluid dynamics. So I ended up in atmospheric dynamics at U of T as well, and spend a lot of my time now in terms of research using like Andre, high performance computing and numerical climate models to study environmental issues. And climate change, but also a lot of my research focuses on ozone depletion and the impacts of ozone depletion on climate. And so I now am assistant professor at U of T in an environmental science department, U of T Scarborough. And actually spend a lot of my time now thinking about teaching and how do we teach sort of the new generation, the upcoming generation of environmental scientists, and what kind of tools and skills are they going to need? So that kind of connects me to the data science, machine learning side of things.
Speaking of teaching, I guess that's how we met. So for the audience who's not familiar with our community or haven't seen this yet, recently we have gotten a decent sized grant from Government of Canada to run a series of workshops and, more importantly, a series of projects for the general public as an outreach program to make people the topics in environmental data science, environmental modeling, and in general how we can use data to make better environmental decisions. And that's how we got connected with Karen, and she's gonna teach these workshops. Do you wanna tell us a little about what's gonna happen in those?
Yeah, sure. Yeah, so I'm putting together in collaboration with Shane Sukan, who's a postdoc in our department, and with Natural Resources Canada. We're going to put together some short videos, basically with the intention of familiarizing people in the data science community with the domain of environmental and earth sciences. So we'll talk about the types of data that are available. What is environmental data or science data, the scale of the data. So what are we talking about? Small data sets, big? Are we talking big data? We'll talk about the structure of these data. We're often talking about data that is very highly multidimensional, right? We think about climate model output. That's data that varies as a function of latitude, longitude, height, time. So we'll talk about that, and then we'll talk about the open source tools, specifically Python tools that are available to deal with data in this type of format. So yeah, it'll be kind of a quick overview, and then these workshops are basically going to lead into these working groups, such that people can get their hands dirty, like start to play with this data and explore machine learning methods that can give us insights into this data. And so maybe Andre can talk a little bit more about the nature of these projects that are coming up.
Yeah, I guess. So we actually have quite a few projects coming up about hydrology-related topics, and maybe I had a hand in picking these topics. So there is streamflow prediction and reservoir volume estimation, and one that's actually really cool is about the impact of wildfires on water quality and water resources. So I'm really excited about these kind of projects. But that's not the only thing. So we'll also have a land cover mapping, so remote sensing and basically computer vision applied to satellite images, land cover mapping project, and geological landform identification. It's sort of a similar approach, right? So computer vision applied to remote sensing is also a big theme. Going back to the hydrology project, so they will combine different methods, either time series prediction or also computer vision or sort of spatial patterns. But these are sort of the two big areas, I guess.
So maybe I think we should still talk a little more about why we care about these projects at all, right? So Andre, I remember from the early days when I posted on our Slack channel, which audience, by the way, there's a link to it in the video description, and you can join if you're not there yet. Uh, you were very passionate about this. You were very excited.
Mhm.
You introduced us to
Right.
Karen. You helped us with the projects. Why do you care about this so much? Same
So
for you, Karen,
yeah,
after.
there there are actually different aspects to this, right? So one is the environmental prediction part, and this is something like weather prediction, for numerical weather prediction. I think is one of the greatest achievements of humanity. um, and I'm happy to talk more about why I think that. But so environmental prediction is one thing I find absolutely fascinating, and so I'm naturally very interested in this. But then machine learning opens a lot of opportunities for prediction to solve prediction problems that were previously, from a numerical physical modeling perspective, completely intractable. So it opens this whole new world for environmental scientists who are interested in environmental prediction. And of course, also environmental prediction then has a huge impact on society. When you think about weather prediction in particular, flood forecasting, hurricane forecasting, and these kind of things, right? So I think this is a really promising area, and there will be a lot of exciting developments.
Mm-hmm. Yeah, no, for sure. I would echo what Andre says. I mean, especially when you think about weather forecasting and weather prediction in terms of, extreme events and hazards. I mean, you think about how it used to be. How did people, prepare for, a hurricane landfall? I mean, it was just this is really quite incredible. And also, thinking about other types of prediction in terms of climate change projections, right? For example, like there was a big IPCC report, Intergovernmental Panel on Climate Change report that just came out this week, and it all kind of relies on prediction of a highly complex nonlinear environmental system, right? So but yeah, these climate models, they are based on physical equations, but they're also based on parameterizations, which are data-driven components of these models, right? And so traditionally, they've been formulated in very statistical ways, empirical ways, but machine learning can really potentially greatly enhance and help us operationalize some of these parameterizations in new and exciting ways. So yeah, I think I'm really excited about this workshop and connecting with the data science community. I kind of dabbled in data science myself for a while, and came kind of back to academia. But I think there's so much potential for kind of collaboration between earth and environmental scientists and data scientists. So yeah,
Mm-hmm.
excited.
And so I've worked with a few data scientists, but I've also worked with people outside of atmospheric science. And one of the things I've really noticed is that there's a particular set of skills that you need to actually work in earth science in terms of you need to be able to work with geospatial data, right? It's one of the most important things. So map data, essentially, right? But then you also need to have some idea of how some of the data is generated and what it represents. And there's a fairly steep learning curve to this, especially with the geospatial data. It's not rocket science, but you have to know a little bit about it. And so part of this workshop, I think, is really to ease this or to smooth this learning curve for data scientists and just prevent some of the possible misunderstandings or like roadblocks that people may see, right, or may experience in the beginning, and that could very easily be prevented by just sort of being pointed in the right direction, right?
Mm-hmm.
And we're providing a bunch of source code and material for people to get started, right?
Yeah, that's right. We'll throughout the workshop series, we'll provide some, short, notebooks to provide examples of some of the tools that we talk about. And then for the projects, there will be some starter recipes and things like that provided as well. So hopefully, well, as Andre said, kind of smooth out that steep learning curve in terms of just, what tools should I use? Like all scientific disciplines, we have our, domain specific tools that are available for doing this type of analysis. So we'll just kind of quickly make those resources available without, having to do all that homework yourself. So yeah.
And the projects are led by some scientists.
Right. Yeah. So we have some people from NRCan and but also some volunteers. And so there are people from. So NRCan is actually it's Natural Resources Canada. If you work in earth science, you know this, and if you don't, then probably not.
This
It
is
has
your
many
chance to
different
learn about
departments.
them, right?
So NRCan has many different departments. So there's, for example, the Forest Service. The wildfire project will be led by 2 scientists from the Forest Service. Then the landform mapping will be led by a scientist, or actually 2 scientists as well, from the Geological Survey. So most people come from different departments of NRCan, but there are also some volunteers that I've worked with before, Jan, for example, who is actually a member of our community here.
Yeah, and maybe for people who are not familiar at all really with this type of data, one of the cool things about it is there's tons of open publicly available data available, right? So typically, satellite, remotely sensed data, even data from numerical climate models, weather forecast systems, this data is made publicly available, sometimes in almost near real time. So it's pretty cool. There's just tons of data to scour through from, I know, in certain domains, and then in other domains we're talking about pretty small samples of data when we're talking about in situ observations, but still a lot of it is publicly available, so it's just kind of waiting to be explored.
And you just have to know where to find it, and this is something we will highlight in the workshop as well. And this is really one of the big goals for NRCan actually in supporting that workshop. I think that they just want to get the information out there about these data sets. Right? But one other aspect of that is, of course, you have to know how to use the data. And there's a long tradition, as I've sort of alluded to before, in environmental sciences of numerical modeling. And processes and formats and conventions have been developed over decades to support this numerical modeling. And these are largely still used, and they learn a bit from or incorporate some advances from data science, but they still exist mostly separate, and it's a different ecosystem to the data science ecosystem. File formats are different. Usually data, I would say, so specifically in atmospheric science, data tends to be highly structured, in remote sensing as well. It's essentially like multidimensional arrays, right? And so there are specific formats that really take advantage of that. Whereas then, of course, in ecology, usually data is much less structured, and so that's more the classic data science case, I think. But,
Yeah, and I was gonna kind of maybe circle back a little bit to your question, Amir, about why do we care about this, right? And so we talked a lot about prediction, and of course, prediction is one of the kind of I guess key use cases for machine learning and AI. But I guess I would say, as a academic, as a scientist, I'm interested also in just understanding the system, right? And how what drives what and what processes are involved. And I think this is another area where machine learning can provide insights. I mean, it's a little bit more, a little bit more work needs to be done in terms of thinking about using techniques in the sort of maybe explainable AI kind of realm domain. How can we gain insights that we maybe used to get using very simple statistical techniques But that's from my perspective, as a research scientist and academic, I'm thinking about those use cases as well, thinking about just understanding the system and how that understanding can also help to inform some of the process-based physical numerical models that we use as well. So there's kind of this back and forth, I think, that can be achieved by collaboration across these domains. So
Very
yeah, I
interesting.
don't know.
So there's a question in the chat that I'm going to address in a second, but I'm going to very quickly summarize what you said and tell me if I missed anything. So essentially what is happening here is that Government of Canada has a lot of data related to natural resources and environment. And there are also other data sets that are available globally that could be used for modeling environmental things. And the purpose here is, from the Government of Canada, is to help educate the public about how they can use this. And when we say public, public who knows how to write Python code and do data science stuff. So that's their motivation. Like, you don't need to bring in any domain knowledge. As we said, there are several scientists from Natural Resources Canada, as well as Karen, as well as Shane, Andre, who are generally available to help you with any questions related to the environmental science and climate and forest and water flows and et cetera, geology. And you are mostly bringing in your data science and machine learning point of view. You don't even need to necessarily be a very experienced data scientist. You might be transitioning to data science from a different field, and this is a very good opportunity to get familiar with real world data and use it to build something interesting. And Sarush is asking in the chat, and I'm going to rephrase a bit. What is the deliverable for this? Like, what are we looking for at the end of this? Like, what will the participants have to show as proof of work?
Andre, you want to take this one since you've been more involved in the project development?
Right. So this is actually pretty open. And so there's actually some projects where we don't even know if it works. So some of them are more experimental. Others are basically just replicating or transplanting a method from somewhere else to the Canadian context. So it varies a bit from the project. So in the projects where we are replicating an existing method, basically the deliverable is just show the application in the Canadian context. In the more experimental projects, we don't really know. Of course, if we actually get what we want, basically, for example, a prediction problem, then that's great. It may not work very well. Then you would just have to show that you worked on it. But the main goal here is just for the participants to really learn and play with the data. It's not so much about actually producing like a deployment-ready product or something like that, right? You're not looking to like actually develop a product. It's a learning goal, right?
Mm-hmm. Yeah, I think that's really the aim, right? Is to familiarize, to welcome the data science community to work on these type of problems. Yeah, so I think if it's something that interests you, kind of just playing around with this type of geospatial data and exploring how this data could maybe be applied even outside of an environmental realm, right? Like there may be some sort of landscape data sets out there that may be useful for some other project that you're interested in. But you kind of need to learn how to work with that data. That this might be a great opportunity to kind of just get started.
Yeah, I think this is actually a very good point, Karen. A lot of these data sets would actually be useful for a wide range of commercial applications. I could imagine like applications in like logistics or urban planning, where the data scientists can have a big impact, but they can even more impact if they know about the environmental data sources as well. And I think this is actually a major goal to not only get scientists into environmental science. I mean, that would be great. I mean, environmental science is generally understaffed and under-resourced, but also to get the environmental data out into different areas where data scientists are already working. Like, I'm thinking about logistics and sort of related things, right? Where you could benefit a lot from better geographic and weather data.
Yeah, and I think that's a great point. And then just maybe like a counterpoint would be that hopefully this workshop and these working groups will also expose participants to the limitations of working with this data. So it's not like a black box data product you can just take and apply, right? So hopefully it will kind of expose you to some of the nuance of working with these data products. What are the data gaps? What are the sources of uncertainty associated with these different data products? So there's both sides, right? So kind of overall getting more familiar with the types of data available, thinking about cool ideas of how you could use it, and then also where, okay, maybe it's not so appropriate. So yeah, anyway, they're super exciting.
So just to build on top of what you said, of course, a lot of what we're doing is for cross-pollination. Karen and I were talking before we went live that one of the unexpected outcomes of AI was to bring in so many different fields together. And, in our very large AI community, we see people from all sorts of backgrounds, but also from all sorts of verticals and industries who are interested to use AI, and then they cross path. And I really like the word cross-pollination that happens a lot in our community because people learn from each other, teach each other. There's a lot of peer-to-peer learning. Like, of course, there is Karen and Andre and a lot of senior people who are coming to these activities and a lot of other activities who are bringing their wealth of knowledge. But a lot of the learning is going to happen peer-to-peer when you're interacting with each other. But of course, we want you to have a proof of work. And unfortunately, we don't believe in certificates. So, part of the purpose is to enable yourselves to essentially build portfolios, right? So we will be helping you to create content out of whatever you're doing. So it could be, a GitHub repository you clean up and shape it up for, if you're looking for a job, or if you have a job, but you're looking for a promotion, moving on to a different company, career movement, whatever. These type of artifacts will be very helpful, like a nice and clean GitHub repository you collaborate with a bunch of other people on, or a blog post that you wrote about something interesting, or on the experimental ones, who knows, maybe so there are opportunities, and you can take it as far as you want.
Yeah, maybe I'll just add, like, one of the cool things about working with geospatial data too is that data visualization can be really, really exciting, right? So in terms of writing a blog post, you could have some cool maps and or there's some these are proprietary tools maybe, but ArcGIS, which is a company that develops geographical information system software. They have these like sort of story map type of blog post formats where you can, I think there's some open source, I think Night Lab has an open source kind of story map as application as well. So they're really cool ways to present your results in a visually kind of intriguing way. So
yeah. I mean, maps are beautiful, right?
Yeah. I mean, we're a little bit biased, maybe.
Yeah, of course they look beautiful to you.
Yeah.
It should look beautiful to everyone. I'm not saying that they shouldn't. So 100%. So there is another question asking. Sorry, I'm looking to the side because my laptop is there with the questions.
Okay.
What's the process of getting in, and what's going to happen when you're inside? So I believe, correct me if I'm wrong, but I believe we are very open and welcoming. Anybody can join. There are links for reading information and signing up for the workshop in the video description. So make sure you click on that and read everything. You can see the details of all projects. Each project has their own landing page too. They're slowly being built. So check those out. We've been talking for about half an hour and we didn't bring this up because, it is a nice to have. Like the point is really learning something new and, at the same time educating your peers and, building something interesting. But since we have this grant from Government of Canada and we want to incentivize you to finish the projects you start, there's also a $500 per person gift that if you meet certain criteria for each of the projects, you will qualify to receive. So, we are helping you learn something, and we are even incentivizing you with a small gift at the end. So I don't really know why you wouldn't participate. If you have Karen, Andre, can you think of any reasons people want to participate? Unless they had a baby yesterday, so.
You're asking the wrong people. Of course, we think everyone should want to do environmental data science.
Right.
But yeah, no, I think I think this workshop and the structure of the workshop, so having some of these introductory videos to kind of get you familiar with the landscape of environmental and earth data science, and then having these scientists from NRCan collaborating with you, working with you on these projects, and they've designed these projects to really kind of explore concepts and explore tools that could be really useful. I think this is a great opportunity to also network with the people who are doing this type of work in government labs, and these could maybe be connections that you could carry forward. So yeah, I wish I could have participated in something like this when I was in my data science years.
Yeah, I think one of the things that you said that is very interesting, Karen, is taking this forward. Like a lot of what we are doing is going to happen over 2 to 3 months, but really the purpose is activating the ability of people to do things. So you're going to make a lot of connections that you will continue building on top of. Like, there's no reason that you wouldn't continue these projects to publish papers and build products and build businesses. You've seen that in our community. Like, we had discussion groups that people started randomly talking about things, and now they're thinking about how can we productize this and raise money for it. And, they're asking me about all the fundraising and grant writing tricks to fund their projects. So think about this as a fertile ground. We are just, pushing you forward,
Yeah. And from an entrepreneurial perspective, this is a pretty new field in a way, right? Like a lot of this type of work has been happening in government labs. It's been funded through in the public domain, but there is an emerging kind of private sector domain doing this type of environmental prediction and kind of how do we optimize different systems for, particularly I'm thinking about like the agricultural sector, sort of optimization problems that exist there. There are different private sector companies popping up.
Yeah.
So, and Andre works for one of those, right? So you can think about the workshop too in that way. Like if you're interested in maybe a career shift or something into this area, this is really an emerging field in terms of private sector.
And I would say this is still a very open field. There are not a lot of companies that operate in this space, and there's I would say that there's a lot of room for different companies and startups to really grow and sort of test out ideas, right? And my sense is there's a lot of interest. So in this, it's really early days, right? So a lot of companies are realizing that there's probably something they can use, and maybe they need to do something about climate change and or get some ready for climate change. But there are also a lot of people I find who are interested in working in these areas, but bringing this sort of together and sort of forming companies and sort of training people in the ability to actually pursue this, right, is a bit of a bottleneck, I think, at the moment, right? And so I think there's a lot of opportunity. And going back to what Karen said before about networking with the anarchan scientists, and yes, these are the people who have traditionally been doing a lot of this work, right? And they sit on all of the data. So if you think of starting a company in that area, it's really good to have these connections, because this is where you get the data and where you sort of get the insights on what already has been done, right? So it's sort of, yeah, like Amir sometimes says, it's an open sandbox where you can play around with things, and it's really exciting. It's a really exciting field, yeah. And there are not enough people who work in this.
Yeah.
I see some excitement in the chat. Talwa Joshua is saying that they have a very interesting background that straddles these topics, and they are very excited to get started in these projects. So we're looking forward to see you. And Diana is saying that these sound very great, and hopefully these are the first of many. That's our hope as well. Even if not, particularly in the topic of environmental data science or our platform in general, I sometimes like to think about it as sort of an incubator, an IP farm. I don't know what you want to call it, the fertile ground where a lot of intellectuals collide. And when you bring in a lot of intellectual people in a room and just let them talk, a lot of good things happen. And if they are unable to have constructive conversation. So I believe if you click on the link that I shared in the video description, you can see a lot of other projects that we are doing that are not environmental data science. But this is a fairly large initiative that we kicked off because it's a very relevant topic. Now let's talk about let's change gears a little, and let's talk about environmental science a little. Let's leave the data out a bit. Although the first time I told my PhD supervisor that I'm doing data science, his reaction was, "You're an experimentalist. You've been doing data. You've been doing science with data for your whole career. So what are you talking about?" Fair enough.
Exactly.
So, but how were we doing? Environmental science before machine learning?
Yeah, well, maybe I can jump in. I mean, we were using more, I guess, traditional statistical methods to analyze data. But in terms of the prediction side of things, I mean, I think we've already kind of touched on this quite a bit, but we, use a lot of kind of physics-based numerical models to make predictions. And that, of course, is not going to go away with the advent of machine learning. But I think there's a very sort of complementary way that these things can be integrated together. But in terms of kind of the science, discovery, kind of trying to understand relationships between things, traditional sort of statistical methods, are some of the tools that we use. And some of them, you can think are sort of familiar in the machine learning language, like, principal component analysis, these types of ways to extract patterns from very complex, highly variable data sets, and ways to reduce those data sets down, right? So principal component analysis was it and still is a very common way to kind of try to shrink the data down into a manageable, index or something like that. So, and I think, I don't know, from a physics perspective, I was thinking about this before we chatted, but like, at least, in atmospheric science, we have these very nonlinear equations, and then we linearize them. and so, like, sometimes, simple linear regression has a certain sort of direct relationship to the kind of theory that this linearized theory that we're thinking about. So it was kind of a nice tool to just kind of think about these linear relationships. But but yeah, we obviously oversimplify things when we do that. So yeah, Andre, maybe you can jump in because you're working
Right.
more
So
in the
there's actually, there's a very interesting aspect of this in hydrology, and it's a bit different. But maybe from a physicist perspective, I'd say in pre-data science, a lot of the methods we've been using are basically linear methods, and we've been sort of struggling with this for a long time. We're using all these linear analysis methods, but we know that the system is actually highly nonlinear. And how does this fit together? And so with data science or with machine learning, I think there's a lot of excitement, especially atmospheric science, to get more towards nonlinear methods or method that can capture nonlinear relationships like various Taylor connections in the atmosphere and patterns that don't fit well on a linear pattern. This is actually a very interesting area. But the other thing I wanted to say is in hydrology, there is something called conceptual models, which is actually very interesting. And these are models that they're built on some kind of physical intuition, but they're essentially highly parameterized. And hydrologists have been essentially doing data science, if you will, or what people do in data science now, for decades. In that they've built these conceptual models, and then just used optimization algorithms to tune the parameters to observed stream flow. And so the structure was sort of handcrafted. So we know that there's snowpack, and snowpack accumulates, and then it melts, and that's temperature dependent. And so there's like a melt coefficient that's related to temperature, and we accumulate precipitation, and then there's a groundwater contribution, which is slow. So we can do like a lag factor on that, and like very roughly speaking, right? And some of these models have gotten extremely complex, right? As you can imagine, with many scientists working on them over decades, right? And so they have hundreds of free parameters, and then they just tuned to fit observations. And this is essentially what a lot of predictive modeling and data science is, right? And hydrologists have been doing this for decades. Now, it turns out that actually modern data science methods, in particular LSTMs, have been incredibly successful in streamflow prediction, but this is very recent. And it's not surprising in a way. It's essentially the same approach, except that you're not handcrafting the structure of the model. And this is actually also one of our projects where we'll test out an LSTM approach on some of the streamflow data in Canada.
Yeah, super cool.
So,
yeah.
Sorry, go on.
No, I was just gonna say, I think like this idea of like parameter searching and trying to find like the optimal parameters for given models, for our large Earth system models that are largely kind of numerical models. We have these parameterizations within them, and then so the same type of approaches are being used and explored in terms of optimizing parameters. And so this is where the sort of data science, machine learning expertise comes in. But then there's I feel like in terms of the collaborative side, what parameters are physically realistic, right? So we need to kind of always have that back and forth between the data scientist and the earth scientist, environmental scientist, to think about, or maybe even constrain that parameter search space, right? Like, to try to make the process more efficient. So that's certainly like a really important use case for machine learning, is thinking about these kind of optimization.
Yeah, and I think you can. There's really a lot of room for collaboration between data scientists and physical scientists in formulating these physical constraints, and also in the context of explainability. So I know in the aggregate intellect community, this is a big topic, AI explainability. There are really interesting papers that talk about, as I keep getting back to these streamflow predictions, because they're really a very classic example where you can really show that the model is learning to represent physical properties of a watershed. Like some of the activations in the model actually correlate with like snowpack and groundwater, and it's like from a scientific point of view really interesting. But you can also I guess learn a bit more about the model, and so explain what the model is actually doing. And I find this really fascinating to see how the model learns the physics, right? But then on the other side, there are also methods to impose some physical constraints like mass conservation on the model, and these are very interesting approaches too. And this is also being pursued now. And this, yeah, I think it's something very interesting where physicists can also sort of help in data science.
Mm-hmm. Yeah. I think it's a super cool kind of landscape in the sense that, we have these physical laws that do offer constraints, right? So it's not just this wide open kind of, unstructured sort of data analysis process. There can be some structure, there can be some constraints to actually make a more meaningful prediction, get meaningful output from a physical perspective. So yeah.
And also constrain it a bit more in the sense that you could probably trust it more if there's an out of sample prediction, right? And this is one of my sort of favorite topics. So in operational forecasting, or also in sort of like weather prediction type of setting, it's basically in sample prediction. You basically you train the model on the historical record, which you assume would encompass everything that you are going to see. But then I'm a climate scientist, Karen as well, and climate change is a very important topic. And so there is this issue that we're using historical data to train environmental models, but actually we are moving outside of the range of that data. And so if you care about climate change, if you're interested in climate change impacts, and you want to use these machine learning models, you're actually getting out of your sample, and then you get a bit worried, right, about how trustworthy the model is.
Yeah, no, I mean, I think that's definitely something that, becoming more aware of the domain that as a data scientist, becoming more aware of the domain and thinking about these things, you think like, what training data should I use is a important, question you ask in the whole pipeline process, right? So, and how does that training data influence the type of prediction that I get? So this is a really important thing to think about. And I guess kind of why I guess I said earlier, that I don't think numerical, physics-based models are going to go away because of some of this. We need some kind of validation, and then we could, we're probably going to have both things happening, right? It's not going to be an either or. It's going to be both, and the these physics-based models will help to validate some of these machine learning models that may be more computationally efficient. Like I know that probably for the data science community might be like, oh my god, computationally efficient, but some of these high performance or these sorry, I should say numerical Earth system models that are run on high performance computing systems, take like a long time to run, and so some of these machine learning solutions may be more efficient and more give us more I guess real-time information or rapid predictions, but yeah.
In terms of compute resources, weather prediction centers and their supercomputers always rank in the top of the top 500. So this is very significant.
It may be hard to believe, but yeah, these systems are hugely computationally expensive, right? So yeah.
Speaking of compute resources, we do have some budget also for the projects that we are running for cloud credits. So if you have some crazy but interesting ideas for projects that might be computationally I mean, obviously not in the top 500, but it could be more computationally intensive than Google Colabs. We can probably help you try those out. So nothing to lose again. So the topic is definitely very interesting, and I think I've brought this up in several of the conversations that I'm reading this book called Book of Why, which talks about how statistics in general, but also machine learning as a subfield. I think a lot of people are going to get very angry that I said that, but from a physicist point of view, they are kind of the same. Yeah, both of these, tools are very good at identifying correlations, and they are pretty much completely incapable of, tracking causations, which is what physics models bring to the table. Because in physics model, we use symmetries to simplify models, create a spherical cows, and use those to build models that generalize very well. Of course, that's why they become computationally much more expensive, because they are trying to cover many more bases, while machine learning models try to find correlations that leverage the sparsity in data and such, and they end up being more effective. But I also think that physical modeling is not going to go away. And it's very interesting to see the interplay of the two. And I think one area that I don't think either of you touched on is synthetic data. So I know a lot of people use physical simulation engines to generate data that is then used to train models, which then feeds into the simulation. And there is a whole interesting topic going on there that, there are lots of interesting advances there. I even have friends who are working on a very interesting topic of building physical symmetries, sorry, not physical, mathematical symmetries into machine learning models. For example, convolutional neural networks have translational symmetry. That's why they work so well on images, because images have translational symmetry. But how about all the other Lie algebra symmetries, like group theory symmetries? Can we build those into models and architectures that then they are more symmetry aware for different types of problems that we are going to work on? So a lot of interesting things to talk about, but unfortunately, we're almost out of time. And hopefully, you're excited enough to join us for this. As you can see, we love talking about these topics. But to wrap it up, maybe Karen and Andre, you can. What's the verdict? What's your take-home message from this conversation for the audience?
Yeah, well, I guess I would say that this is a relatively emerging new field, and a great time to kind of get involved and think about the different applications of earth and environmental data, and think about different methods to explore it. So yeah, I mean, as I mentioned off the top, we had another very grim IPCC report that came out this week, and there are lots of environmental challenges that we're facing, and already facing and will continue to face. And, we need kind of all hands on deck in terms of how to develop solutions and make predictions for adaptation to climate change and those sorts of things. So, so yeah, if you're interested in those sorts of topics and you have, your data science skill set, then this is a great opportunity to explore that possibility.
Yeah, I think I can only echo that. It's obviously a very important topic, but it's also a really interesting area. And there is a lot of opportunity. There's a lot of data that has not been exploited. So there's a lot of work to be done, and we need more people to work on it.
Yeah.
Definitely.
So March 10th, I think next week, you can mark your calendar, is the first kind of live Q&A session for the as part of the workshop. So so check it out, and we'd love to see you there.
Definitely. I'm going to quickly share my screen to show something that I shared in the show description. And we're going to add a little more details to this. But so there's a recipe that contains this video, as well as a few other resources that you can check out related to all of the topics that we talked about. You can consider that as the initial reading material to prep. And there is also, there is this video that we talked about with some of our notes about stuff that we talked about, but also the link to the workshop and the details, about the gifts that I mentioned that I would reiterate, when it's going to start, and all of the details of the projects, but also a bunch of other reading things. For example, how Google has used AI to predict floods, and some other things that we will add as sort of the reading material to get you warmed up while you wait for the workshop videos to come out and you can get started. But please do join our community and join this effort. It is one of many things that we are doing. This is probably the most significant one that we are currently doing. But definitely join our Slack channel. The link is in the show description. Check out the material and the recipe that I showed. Check out the link to the workshop and sign up, and we hope to see you there. Thank you so much, Sharon and Andre, for joining me today. It was such a fun conversation. I had missed talking to physicists. And it was
great.
definitely fun. Thank you so much.
Yeah, thanks,
hope
Amir.
to see you in the next session.
Oops, where's Karen?